Let's introduce a collision in which one object is moving, okay, we'll call it object A, and the other object's at rest. Okay, so we have V, A, initial. The other object's at rest. So they collide, so that's the before picture. Remember, it's the just before. All we're considering is the moment, the absolute smallest moment right before these two collide. So A may have been slowing down prior, but we're talking about the velocity right before it collides. Okay, and then if we look just after that collision, so our delta t is super small, we can neglect any external forces. What's going to happen? All right, now it depends on how they interact. So we saw in a previous video, we saw how an inelastic collision is one in which they hook together, stick together like two balls of clay. They stick together and move together afterwards. We're going to now consider the elastic or perfectly elastic condition. Okay, and that means that these two will bounce off, but in a specific way. Perfectly elastic perfectly elastic means not only is delta P 0, but delta K is 0 as well. Okay. Now, not very many, so delta K is the kinetic energy. So it's meaning that the total kinetic energy to start is the same at the end. Now, there are not very many real-life situations that can be approximated to this. There are no real-life situations where this is totally true, 100% true. But there are enough real-life situations where this is close to be true. If you just drop a bouncy ball, it's decently true, but not even then. If you drop a bouncy ball, it doesn't come up to the same height, which would be the case if it had the same kinetic energy after bouncing. But it's close. It's not too bad. The better the bouncy ball, the closer this is. Okay, so we call it a perfectly elastic. So this is an ideal case. It wouldn't happen very often, but we can approximate many things to it. Okay, so perfectly elastic is not only is momentum conserved, but kinetic energy is conserved too. All right, now momentum is conserved in any collision if we're careful to measure just before to just after. If we wait too long before or too long after to measure our velocities, then this isn't going to be conserved because then those forces had time to act. But remember, just before to just after means delta P of the system equals 0, or momentum of the system is conserved. Okay, so with that clarification and review, with this new type of collision, delta K is 0. And so what seems reasonable is that A and B would be moving afterwards somehow. Okay? Now I'm not going to draw vectors yet because we can come up with a variety of situations that could say A will continue forward or A will bounce backward. B might continue forward. It would never bounce backward, but it may not go anywhere. It just depends on how heavy A and B are. Okay? So the way to describe that means we have to do a derivation. We have to use this equation, and we have to use this equation. Now the derivation is given in the text, and it's available there. And I don't want to spend time focusing on that derivation, but just know that you start with this, and so you'll have a VA final and a VB final. It always assumes the equations given assume that VB initial is 0. So it assumes VB initial equals 0. All right. So it starts with this, uses this, assumes that, and you can find VA final and VB final. What I want to do is focus on the results. Okay, what you get is that VA final is equal to MA minus MB over MA plus MB times VA initial. And you get VB final is equal to 2MA over MA plus MB VA initial. So they're both a function of the initial velocity of A, because that's the only velocity there is to start with, and then a function of their masses. Okay, so again, the derivation of these are in the text. I want to focus on 3 specific cases. Okay, let's take case 1 to be M1 equals M2, or sorry, MA equals MB. All right. If MA equals MB, what happens? Now, let's cover up these and let's think logically what would happen. From your experience, if I roll one ball and it hits another ball, there would be really stiff balls like billiard balls are great examples. So ball A hits ball B totally elastically, so our kinetic energy is conserved. What happens? Now, first of all, billiard balls have equal masses. Okay, so what in my experience, if I roll a billiard ball, then A hits this one and A stops. Nearly all the time, it just stops. And B continues forward, and B looks like it continues forward with a similar speed to what A had. Okay, and so we should maybe expect that the final velocity for A is 0, and the final velocity for B is equal to the initial velocity of A. That's a reasonable assumption based on just intuition and experience. Do the equations give that? So let's look here. The velocity of A, if MA equals MB, then MA minus MB is 0, and yep, the final velocity of A is 0. That's just what we guessed from intuition. Well, what about the final velocity for B? We said that it was going to move forward with about the velocity of VA. And so if A equals B, then we have 2 times MA over MA plus MA, which is 2MA. These cancel, leaving us 1, and I have VB final equals VA initial. So it's true. It matches correctly. All right, so that would be the case for them having equal masses. All right, let me actually draw this. So that we'd have A stops, okay, VA final equals 0, and B moves on with VB final equals VA initial. All right. What about the next case where the mass of the first ball, A, is huge compared to the mass of B? Sorry, I didn't make that M very good. MA. So consider it's like a bowling ball hitting a ping pong ball. Okay, so again, think logically. What should happen if a bowling ball hit a ping pong ball? Bowling ball's moving, ping pong ball's at rest, bowling ball hits the ping pong ball. Now what's going to happen? Well, do you really think the bowling ball is going to even notice the ping pong ball? No, probably not. So the bowling ball ought to move forward with the same speed it had without stopping. Okay? Now the ping pong ball ought to be shot off pretty darn fast. How fast, I'm not quite sure, but it should move forward quite quickly. Because if this isn't stopping, then this has to be shot off ahead of it. So this should have a speed that's faster than the bowling ball. Okay, so that's what our intuition says. If the moving object has much greater mass than the stationary object, then the moving object should keep on moving without changing speed, and the stationary object should move off faster. Okay, so let's see what the math says. So if MA is much bigger than MB, so like this is 1,000,000, then that's 1. Well, 1,000,000 minus 1 is basically 1,000,000. So basically we can say this is just MA. Okay? Well, 1,000,000 plus 1 is basically 1,000,000. So we can really just ignore those two terms, and we just have MA over MA, which is just 1. Okay? And so to this approximation that MA is huge compared to MB, then we got that the final velocity of A is equal to the initial velocity. It just keeps on going. Okay, so that checks. So we'd have A just keeps on going, VA final equals VA initial. All right? We're assuming B shoots off with a high speed. VB final. What does it equal? Should be bigger than VA initial. What do we get here? Well, MA plus MB, again, to this approximation is just MA. And so I can ignore that MB down there. And I get 2MA over MA is just 2, because the MA's cancel. And so what it says is that not only is it faster, it's twice as fast. All I'm left with is this 2. So VB final equals 2 times VA initial. Okay? And so this is actually twice VA initial. So the 2 I wasn't able to guess just from making an intuitive guess, but I knew it should be faster. And here the theory says it should be twice as fast. So if we didn't experiment with 2 billiard balls, which are really close to a perfect elastic collision, then we would be able to find to very good precision that the final velocity of B is twice as fast as in an initial velocity A. And I should clarify, that wouldn't be for billiard balls. It would be a bowling ball hitting a ping pong ball. Okay? All right, one last approximation here is 3. What if MA is now really light compared to MB? So that's like a ping pong ball hitting a bowling ball. So what would you expect? Again, covering up our theory, what would intuition tell you? So if a ping pong ball is hitting a bowling ball, do you expect the bowling ball to do anything? No, not really. I mean, the ping pong ball just bounce off. So the ping pong ball ought to bounce off and probably come backwards with the same speed it had before. It's just going to bounce off like I bounced it off the floor. And the bowling ball probably won't do anything. Okay, so let's see what that says here. Here's our ping pong ball hitting a bowling ball. So the ping pong ball is super small compared to the bowling ball. So something small minus something really big is basically a negative something really big. It's basically 0 minus the number. Okay? So 1 minus a million is basically negative a million. All right, now 1 plus a million is still basically a million. So we get negative a million over a million, or negative MB over MB. The MB's cancel, and we just get a negative sign. And so indeed, our lighter object that was moving just bounces off and goes the other direction with the same speed. So we get VA final equals negative VA initial. Well, what about MB or VB? Okay, remember, MA is super small compared to MB. So MA plus MB is basically just MB. Now MA is super small compared to MB. So a small number divided by a big number is basically 0. 1 divided by a million is a millionth, and so that's pretty small. And so this is basically 0, and we have VA or VB final is basically 0. So VB final equals 0. So the derivation is really useful, but what's more important is knowing that we got it by applying conservation momentum, which can happen as long as we choose a narrow enough window, which in a collision, that'd be just before the collision to just after the collision. And then also assuming, and this is usually an assumption, not an exact thing. This happens if we choose appropriate window. This is an assumption. It's not always true, or it's definitely not exactly true. But it's usually a good approximation. So using those, we can derive these, but then we made sense of these. And that's what's more important. Okay, now before we leave this video, I want to emphasize that this is a pretty narrow discussion. These equations are pretty narrow. They're not, you can't use them for a lot of different scenarios. It assumes that, first of all, it assumes a perfectly elastic collision, which itself is a narrow window of problems. But it also assumes that the velocity of B is 0 to start. Well, how often are two things colliding and one of them is not moving? Well, that does happen, but it'd sure be nicer if we could apply this to a broader number of problems. So what if we do have a situation where B is moving? Let's say it's moving a little slower. It'd have to move slower in order for them to collide. What if we have something like this? Well, we can't apply these equations, at least not as they are. But we've seen before about reference frames. And I could choose a reference frame with respect to B, meaning I'm going to measure everything relative to where B is. And if that's true, then the velocity of B with respect to B is 0, which satisfies the condition where these equations were derived. So it just means A, the velocity of A that I actually use in these equations, I change based on our relative frames. And then once I get my answer, I'd have to change it back to the reference frame of our standard or stationary reference frame. So for example, if this was 1 meter per second, and this was 3 meters per second, then what I would plug into here would be 2 meters per second, because the relative speed between these is 2 meters per second. 3 minus 1 would be 2. So I'd plug in 2 meters per second, 2 meters per second. I do these calculations, okay, and then let's just say that this I get for this afterwards as being 2 meters per second, okay. Well, then I would have to add it back. That's actually going to be 3 meters per second, because it's 2 meters per second relative to this ball, but this ball was moving the original reference frame 1 meter per second. So that means my final would actually have been 3 meters per second. Okay, and so we can use these reference frames to use this problem for any two speeds of our initial objects. So that makes this more powerful. That can expand this to be used for a lot of different problems. Still, remember that kinetic energy is assumed to be 0 for this case.